Alright everyone, welcome back to another video. There we go. How are we all doing today? So today I want to make a quick video on the discrete Fourier transform. We'll try to do a little bit of computer assignment 3. There we go, which is basically the discrete Fourier transform. So from what we've already learned from previous videos is about the continuous, aka the analog Fourier transform, or Fourier series, sorry. And that's basically if we had let's see, a signal f of t, which is basically, you know, some sine wave or some random signal, I think. Basically, if you wanted to take the Fourier series of these or find the Fourier series coefficients for this, we would have some Fourier e to the j omega, where omega is sampled basically at 2 pi n over capital N. We can basically say, okay, this we can recreate this signal using just a bunch of points, like let me just get another marker. Here's our DC term, and then some points right here and points right there, and we would use these couple points to recreate this, and the Fourier, the projection, the time is going to basically equal summation from however many signals. It's going to be from n is equal to n minus 1, actually divided by 2 to n is equal to 0. It's going to be a finite amount of signals of alpha of n. I don't think so. I think it should have been k. Keep the e to the minus j omega k over, no, actually 2 pi k over, and there we go. That's how everyone's used to seeing it. And we would use a couple points to recreate this original time signal, where each of these points are continuous e to the j omega. Actually, I think this should have been time. But point is, that's what we were doing for the past couple of weeks. Now what we're going to try and go to is to the discrete Fourier transform, which is basically if I had some signal, which is, I don't know, f of n, which is just basically, I don't know, it's a couple points, maybe a point right here if you wanted to, and we were analyzing it, x of n, from n is equal to infinity, analyzing the entire signal, e to the minus j omega n, and this formula right here would give us e to the j omega, would give us it would give us the discrete time Fourier transform. And what does DTFT mean? It's basically, let's look at this signal, this cosine signal or sine signal. If we wanted to look at the actual Fourier transform, actually, let me just do an example signal. This one's easy. F of t, which is basically a square. It's basically a square. Therefore, the equivalent Fourier transform, e to the j omega, is going to be this happy sinc function, which you will all see a lot more if you go to grad school. There you go. You'll see this Fourier transform, and it's just, we're analyzing the entire signal from infinity to minus infinity, entire signal, and then we're converting it to a Fourier transform, which is going to be, this is a periodic, we're looking at every point in time. However, if we were to do the discrete time Fourier transform with this, let's say our example signal was, well, this, let's just draw purple, there we go. We were to analyze f of n, therefore the discrete time Fourier transform, so the Fourier transform for discrete signals is how you say it, but you see, this is all engineering lingo, is basically we're going to look at this sinc function, and let me just oh yeah, we're going to use a lot of colors today. We're going to look at, let's sample it here, there we go, right there, and maybe one point right there, then maybe a point right there. I'm just trying to make it look like that. And then there's going to be a point where we're like, I don't want to do all this. So the discrete time Fourier transform, let's put our condition. Omega is equal to 2 pi, k, I guess, divided by n. Where here's our sampling, or how many samples do we have. And this final point, depending on what point we end at, let's just call this one omega is equal to pi, and then this right here is going to be omega is equal to minus pi. And then this series basically, well, it repeats, and then you'll see like this, let me see, comes back like this, and we can see this type of periodicity. It just repeats every 2 pi intervals, every 2 pi. So now for the big granddaddy of this, what is the discrete Fourier transform? Well, there we go. We can't, for the discrete time Fourier transform, this is a lot of points. If we take this n to be infinity, then we're just basically looking at a lot of signals in between this. That's impractical. So we're just going to look at a few points, which is basically 1, 2, 3, 4, and 1, 2. The discrete Fourier transform. And we're just going to look at just a few points, and that's it. And actually for a finite signal, so x of e to the j omega n, where we actually sample 2 pi n over n from n is equal to lowercase n is equal to n minus 1 to n is equal to 0 of x of n. This is a finite. And it's it also is periodic. I think, yeah, finite and periodic. Where this one right here is for infinite and aperiodic. And the analogy I want to make with the discrete time Fourier transform is, look at this. If we're going to look at this, just this square from t is equal to infinity to t is equal to minus infinity, we're just looking literally at this. The Fourier transform is, well, this guy right here. This is also infinite, and it's also aperiodic. And this right here, actually, where do I want to write this? Fourier transform. Oh, this paper is getting messy. Fourier transform is this right here. So let me circle this. This right here and this right here are all related, where it's for infinite signals. So we're just looking at this, whereas the discrete Fourier transform and the continuous Fourier series are just basically short sampled signals, and we're just looking at it for a small amount of time or small amount of memory that we want to store this. So now that I got that out of the way, I tried my best to explain that, but you'll learn more about the discrete time Fourier transform in DSP, where you learn to see, oh, you see this like periodicity, which is going to be related to a unit circle, or relate to Z transform. And that's a surprise tool for later. So the next thing I want to see if we can do, let's grab another piece of paper. Actually, if you don't believe me about what I said about the discrete time Fourier transform, let's think about the, how do I want to do this? Let's think about the Laplace transform. Laplace in the S domain. There we go. So if we have some signal that we want to map into the Laplace domain, we would, well, plot whatever you want to. However, remember how we can go from the Laplace domain to the Z domain, which is Z, well, S is equal to, actually, no, do I want to explain that one? Actually, let me try to explain this way, where S is equal to just the real part. So if this was the Laplace domain, S, this is going to be the Fourier domain. However, to get to the Z domain, there we go. The Z domain, we're basically going to wrap this entire thing, imaginary axis, like this. And then you'll get the following. There we go. You'll get this big circle, and basically your Fourier series is now going to look like, there we go. If I were to draw this as omega is equal to pi at this point, this is omega is equal to 0, and then omega is equal to minus pi. That means points that are on this circle. So if I were to put this, or random points on this circle, where omega k is going to equal to 2 pi k over n. So if you increase n, if you increase the number of samples, therefore this term gets big, this entire term gets small, the precision gets smaller, which means you get more points, and that's exactly what I'm trying to get to you with the discrete time Fourier transform. So basically this discrete time Fourier transform maps like this. So if you want to think about it, if you wanted to draw a whole bunch of points, you get the D, T, F, T, which are these mini points if you wanted to wrap it around, and they would go around in circles. So that's the relationship I wanted to go through. So hence why, if you wanted to go from what do you call it, the Z transform to the Fourier transform in a snap, I think the rule is, I don't remember it, I think it's Z is equal to E to the J omega n, or whatever you want. You can punch this in, do your Z transforms, and you can get the same thing with the Fourier transform. So now that I got that established, you're probably saying, hey David, what do we do now? So the next thing I want to do, let me grab this guy. We're recording, yes. I want to go through this really quickly. Oh yeah, I'm watching stupid videos too. There we go. So if we wanted to do exercise 1, let's see. Without using MATLAB, derive the Gramian. So let me just get this right here. Our bases. I'm just writing this on a piece of paper. Let's do the first one. Cosine 2 pi n kn. There we go. And camera. There we go. So the point of this first thing is to basically prove that the basis set has or the Gramian is basically a square where it's a b of 0 dot inner product with itself, b of 1, b of 0 dot dot dot, b of n minus 1 to b of 0. That's bad. This right here is b of 1, b of 1. This is b of 0, b of 1 dot dot dot. Oh, nope. There we go. B of n minus 1, b of n minus 1. There we go. So the point of this is to prove, well, we want to solve for every value given whatever k or however long of a signal that we have. Let me just verify I actually have the right thing. There we go. Oh, capital N on the bottom. Oops. There we go. So to prove this first B0 and B0 case, and we're looking at discrete signals, so we're looking at a n, so our b of k, which is a function of n. So if you wanted to do this, b of 0, be a 0, well, that's easy. Just set this k to 0, and guess what you get? Actually, there's a condition we gotta follow. Oh, what's the condition? Don't want to make this video too long. 0 to n minus 1. So from 0, n minus 1. So n elements is what we're looking at. N is equal to n minus 1 to n is equal to 0. Well, at the first point, well, we're just going to get 1 because that's what cosine is at cosine 0. And then 1, which is going to equal, well, if we add 1 n times, what do we get? N. There we go. So that means, and there's a property I could show you, but you're going to prove that this right here is n, and you're going to prove, so every time cosine, the inside value becomes 0 or pi, you're going to get this condition where cosine is equal to 1 and you get this n. However, there's a special note. What if cosine is a different number? Let's see, b of 1, which is equal to n, lowercase n is equal to n minus 1, n is equal to 0. Cosine, let's actually do it for any k value. Cosine 2 pi kn and cosine 2 pi kn of n. There we go. And this is a special rule, I think. Let me see my little notes. There we go. Where I think it's going to be n is equal to n minus 1, lowercase n. You're going to have a special mixing problem, which is cosine. Let me remember it. This is why we have the holy video notes. There we go. Is this it? Discrete Fourier series. Aha. Actually, no, this is a different proof. Read the book, everyone. Ah, there we go. So, yes, this is the doubling thingy. So, the trig identity that we want to learn is if you have cosine squared of phi, I guess, then it's equal to 1/2 1 plus cosine 2. There you go. This is your simple doubling formula. So that means this inner thing is going to be cosine double this. It's going to be, do I want to do this? Yeah, let's do it. 4 pi kn for n. And oh yes, let's just look at the holy book. This is why I love the book. There we go. 2 pi 2 kn. Oh yeah, he goes into the what do you call it? The Euler domain right here. I'll just write that out for you. Actually, do I want to do this on another piece of paper? Yes. Actually, what I write? 1 here, 2. There you go. This video is already at 18 minutes. Sweet. I want to keep it to 30. 3. So writing back to where we were, we're going to go straight into the Euler domain. That's 1 is equal to 0. What happens when we add, actually, oh, I forgot one thing. Divided by 2. There we go. What happens when we had 1/2 n times? We get n times 1/2, which is okay, that's the reason why I wrote it here. 1 plus cosine 4 pi kn n divided by 2. When you do this, you get n divided by 2 plus, and I guess let's go into the Euler domain. So the rule for this is, let's put the 1/2 here, and we're going to have the 1/2 due to the Euler property, e to the whatever is inside j, positive j, that's how I write my thing, 4 pi kn divided by n, plus e to the minus j 4 pi k n. Oh, camera. There we go. N. There we go. So that means the 1/2 gets outside. And then this is equal to n over 2 plus 1/4. And if we have a finite signal, let me remember this. 1 minus e to the j 4 pi k. Is it really? I think it is. And yes, I think so. 1 minus e to the j 4 pi k. There we go. Yes. Which is that first term. Yep. Then plus 1 minus e to the minus j 4 pi k n. I think I'm on the right path, actually. E to the minus j 4 pi k. Because this n has to disappear some way, because if n goes to infinity, you see what I'm trying to say? Okay. Go back to the holy notes. Oh, I was on the right path. Yep. Oh, wait, no. I flipped it. See that n right there? We were close. Actually, no, wait. Oh, yeah, I did flip it. Okay, there we go. Oh, and I know exactly why. So basically the rule for this is we're going to take this however many elements, which is if n was equal to 10, we're going to have 10. Here's a 10 right here. 10 divided by 10 gives you this 1. There you go. There you go. That looks much better. I flipped it. Point is, as this element gets bigger, well, this has to eventually disappear. But here's the thing I want to tell you as we, what's it call it? You see this value right here? This is 4 pi k. Every time k cycles, like 0, 1, 2, 3, e to the j 0 is 1, 1 minus 1 is 0, e to the j 2 pi is 1, etc. So that means this value is always going to be 1, therefore this is always going to be 1, and then always going to be 1 here too, same thing. Therefore, this whole thing turns to 0, and then you get n divided by 2. And now you can say, okay, depending on how big my square is, we can say this is going to be n, n divided by 2, dot, 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 up to whatever you want. And then the thing for homework is, the cool thing about these basis functions is that they're orthogonal. And that's the whole gist of the entire semester. When you have orthogonal signals, if you try to convolve different numbers, any different numbers right here, like 1 and 0, they're not going to match, which means they're always going to be 0. 0, there we go. Which means if you wanted to multiply this n by n square to some n times 1 signal, let's call it alpha, that means you're going to get this is going to add actually, let me do this, alpha 0, alpha 1, dot, 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 alpha n minus 1. There we go. If we were going to add this, it's going to be, if we had a new signal, n times 1, this plus this, see, this plus this plus this plus this. You see, alpha 0 times n, then this. You see, it doesn't, they all add up to 0, so that means you're going to get this final one, n alpha 0, then n divided by 2. Yep, I think n divided by 2, alpha 0. And this feels weird. But point is, you're going to get this big vector. So if you wanted to do something in MATLAB where you just make this a vector, you can. Dot, dot, dot. Here we go. Let's see. what is our next thing? So if you want to prove that this is 0, well, you can read the book for that one. I assume everyone can do that one. Actually, here's our little homework. So for all the cosine basis functions, the rule you need to remember is at k is equal to 0, the first point, you're always going to get n. And then everything else is n divided by 2. And then the final point, which should be this n divided by 2, it's the cosine pi term. Once you get to the, the cosine, this right here, this will give you that cosine pi term to get this condition, which gives you that endpoint n. Since for the sine case, pull that piece of paper out, we start at something that's not 0, and we don't start at the final point to where this is sine of 0 times sine of 0 is going to be, we don't do that. So this is always going to be n divided by 2 no matter what. And then this guy right here, I'll give you a hint. Every time you multiply its basis function to itself, you're always going to get n. It's the same case like this, but I'll let you figure that out on your own. So once you have that, you can do a bunch of stuff right here. So actually, I want to get right into the MATLAB. It is 26 minutes. Here we are. So I generated a couple points. Let's see, let's run this. Created 2 signals. Do we want to plot them? Yeah, let's plot them. Did you know that you guys can do another thing right here? Figure 1. Here we go. And then plot x. And then, oh, look at that, surprise. Actually, I don't want to plot. I want to stem x. There we go. You didn't know you can do that? Lots of tricks I got under my sleeve. There we go. So you can see this right here looks like a sine wave, right? And I'll do stem y. And then look at this. This one kind of mimics a cosine wave, right? So let me check the assignment. There we go. So you're going to realize for your basis functions, if we were to do this basis function, what's his name? This cosine for x. Darn, I should actually made another one. Okay, let me show you some advanced MATLAB. Title x, our signal x. There you go, you see? Feels great, right? And then figure 2, and then plot, nope, stem y, and title y, our signal y. There we go. Boom. You didn't know those tricks, right? So back to what I was trying to say. This cosine right here, when if you use a basis function that's a cosine onto a sine, you're never going to get an alpha unless it's complex. They'll change this cosine, they'll force this cosine to look like a sine. You'll never get that unless you get like some weird phase changes, but you'll see that some of these signals are going to be like, oh, you're going to use these basis functions, but you get like nothing, you get flatlined. I'll show you an example. And you're like, oh, did I do it wrong? Some basis functions work better than others, and that's why when you use this right here, this one covers cosines and sines. So let me show you what I mean. So right here is our exercise, and this is not the solution you should be doing. This is like basically, okay, we want to like go really raw on this code. So I'll explain what's going on, but the assignment asks to, what's his name? To use your results. So I already gave you the answers, and the answers are here. This is for cosine. Sorry. For cosine. And then sine is going to basically equal, well, n divided by 2, dot, 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 n divided by 2, this is 0, 0, 0, 0, 0, 0. There we go. That's sine. And then the exponential is going to be, well, n, n, n. And there you go. These are your answers for number 1, but you have to prove them right here. So that should get you really started with it. But point is, I'm doing this to prove a quick point. So what was I doing here? Let's see. Numbers of bases. So if we're gonna do this one, I want 3 bases functions. We create a bases, allocate memory. Then we're looking at, oh yeah, this is another way of averaging. So what I'm doing is, you know the summation signal? Or, okay, I'm gonna do something cool. Darn, I can't do that. Nope, come on, David. Oh, wow, cool. I'm gonna do something cool. So we know our inner products, k, b of k, right, is going to equal some summation of, let me see, one basis function, so basis k times basis k, not in complex conjugated though. So what I'm doing is literally getting, let's do this, n is equal to 0, so we're looking at the 0th point. So here's our time, literally time, n from 0 to n minus 1. We're looking at all the elements in the cosine. This is going to go up from 1, pi over 2, whatever this is. But point is, it's going to cycle through that. And look what I did right here. So the reason why I set this to 0 is that initially, this is 0. Which means we're adding the current value is equal to, or the next value is equal to, well, whatever is at the current value plus whatever is already in the memory cell. So since this is 0, we're just going to get this back, and I will parentheses this, run that, and let's look at our bases. Oh, look at that. We got 10, 5, and 5. And then this e to the minus 16, don't be OCPD about it. It's 0, so don't worry about it. But you see how this one starts at 10, 5, 5? Ooh, looks pretty cool. You know what? I'm going to do this guy right here. Look at this. So let's do 6 elements. All right, because we have 0 to 5, that's 6. Now let me show you this, and you're going to be like, wowzers. 10, 5, 5, 5, 5, 10. And you're like, whoa, that's how you prove your work. So now you know what's going on. Now let's look at this one. So the product, I allocated some memory. We're going to create an alpha. Okay. Oh yeah, I did the same thing here. So our signal itself multiplied by, well, whatever this is, or basis function, sorry. This is all an averaging thing. And then if it's an averaging, actually, nah. There's a weird case because some people want to scale the alphas. Don't worry. This is going to be that, what do you call it? Let me show you. Aha. The alpha of k is going to equal to f of n, b of k, divided by b of k, b of k. So we're literally creating a bunch of vectors. There we go. So that's how you would do this. And okay, I'll do this. I want to get to the fun part of this class. Then you get these alphas. That's very interesting. All right. Now let me check this. So what this is that I'm doing right here, I think. Yes, I know. I think what I'm doing. So, you know how we have that kn term? Let me see. Kn. So what I did was we're gonna create. We're gonna pump. Okay. How do I say this? Let me just write another piece of paper. It's 3. It's 4. Oh, we're already at 35 minutes. So eventually we want to do f of n is equal to alpha 0, b of 0, n. We want to cycle this n all the time. However, this n is associated with a k. Let's do this plus alpha 1, b of 1, n. This is going to be length of 10. N is equal to 10. Length of 10. However, at a specific k value. So what I'm trying to do is, with this guy right here, this one's creating F9. Actually, I don't know if I can F9 that one. We're creating a time signal for this basis set, and we're creating respective k's. F9. There we go. So if I were to do this, we're going to do alpha 0 dot 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 alpha 5 b of 5 of n. So we're literally creating 6 of these things, 6, and they all have this length of time. So that's the reason why I did this. And then all you gotta do is, well yeah, this creates this. This is gonna create okay, actually I'm very interested in this one. Let's do this one. I can't F9 that one. I don't know if I can. There we go. KN. So you can probably see something cool, but actually I want to run this one. Basis and there we go. You can probably see this is at k is equal to 0. We have a DC, then we have different functions. Kind of want to plot them. Plot. Okay. Figure 3. There we go. And then stem basis n 2. No, wait. We want the entire row of number 2. There we go. And then look at that puppy. That's that basis function. And then let's do basis 3. See? Pretty cool. And we get faster frequencies. And that's basically what we're trying to do. However, we got to multiply these guys, all these columns, by their respective alphas. So if this is going to be multiplied by alpha 0. This is going to be alpha 1, 2, 3, 4, 5. So now you're seeing the gist of it, right? This basis of n, I'll write it right here. Good thing I can double screen this. Basis of n, basis n, I'm going to call it, which is going to be n minus 1 by k, yeah, k, because that's how many basis functions. Matrix multiplied by alpha, which actually, this is our time. We want our time, and we want this to be there. So that means if this is time, we want to keep time, and we want to make sure the ending is 1. Therefore, this has to be 1. That means this has to be k. There you go. So we need this vector cross product with this vector, and you're going to get this like cool flip of where you get your final product, which is your projection, which is basically an n minus 1 by 1 signal, and then you can plot this there, and that's exactly what I did right here. Oh yeah, run that puppy. boom. And you're saying, oh, yo, David, we actually get a value. And I'm like, remember what I said? We're actually mapping x. And look at this, 10 to the minus 16th. How are you going to get a sine from a cosine? You can't. Like, look, you're always going to get this cosine. This is the basis. It always looks like a cosine, but this is our actual signal. And we're never going to get that. So I'll show you with 3. There we go. Run that puppy. See, you're never going to get... We're using the cosines right now. And you're never going to get a sine. So here's the sine case. It's the same thing. We did the same mathematics. This code, you have to replace it with your own code. So this is not the answer. If you put this as the answer, well, it's good to check, but why are you going to... Like, you need to know how to do this by hand. So, and it's on the exam too. So know what orthogonal signals are, and you should be fine. But just doing some demonstrations. We're going to map a sine to our input. We want, look, this is our input signal, and we want to map it. So, boom, there you go. Actually, what's this look like? Figure 1. What am I doing here? There we go. That's our projection, but why didn't I will do this, because I like the easy life. Boom. There we go. Let's call it 34. And because everyone's probably barking at me saying, I don't know what's going on. Title. Projection. Okay, let's not be lazy. Copy. Actual signal. There we go. And look at that. With 2 basis functions, let's see how close this guy is. Touch that guy. 189 and 2. So if we use more basis functions, I think this one's going to be 4. And then boom, you get pinpoint accuracy. So that's the whole point of doing this. So now you know how to do, well, these guys. And now looking at this, what did I do here? Yes, so this is the fun part of the class I wanted to get to, and that's the fast Fourier transform. So I think I try to create an example here. Let me just turn that back to 1. This is a surprise tool for later. Let's create, let's comment this out. Let's run this. Yes, this is a surprise for later. So we took our input x. So actually, let me just tell you what's going on. So, and someone's probably in the back saying, "Oh, I don't know what's going on, man." With the exponential bases, remember that when you do bases of k inner product with itself, you're going to get n minus 1 to 0 is equal to 0 of e to the j 2 pi n, kn divided by n times minus j, because it's complex conjugated, 2 pi kn divided by n. There we go. So remember this, and I'm about to show you that right now. You want to see this? Boom. Here's your bases, and here's the complex conjugate of it. You could put this minus 1 there, or you can type in conj, the conj function, which is conj of that. But you don't have to, but don't do this. You're going to have to do, your answer is literally, where is it? This. So actually, if you don't believe me, actually we already proved this. Where is bases? Basis. There we go. Actually, let me actually click this. We're gonna look at the basis functions of the exponential. series. There we go. 10, 10, 10, 10, 10, 10, 10. And you can see all of them are 10, or the length of the actual signal itself. So if you don't believe me, there, I already gave you these solutions, but don't do this. You're going to have to replicate this as a vector itself. Explained right. Where's the camera? Right here. So this is literally your solution that you got to punch into MATLAB. Okay, that's all you got to do. Once you get those basis functions and then multiply it to your alphas, boom, you're done. You can go home and sleep. Do the same thing here. And point is, with the exponential basis functions, you can map any function you want. Let's close all. There we go. Let's run that again. And now the cool thing I want to get to, and this is the reason why we use the Discrete Fourier series, or Discrete Fourier Transform, is this right here. And you're probably saying, hey David, well, what's going on? Why do you have all this? So I want you to look at this signal and tell me from this, what can you do actually? Okay, I'm just gonna do by example. So what's going on is, you see this point right here? It's like literally like a 1, and then maybe you see a baby point right there too, and then you see how it like mirrors for some reason. Now let me show you something, and don't let Dr. Steve tell you, or I'll tell you about this, or don't tell him about this. But wait, is that supposed to happen? Clear var, and quick, n is equal to 10. Boom. 2 pi f. Oh, that's probably why I did this. There we go. Wonder why I wasn't running the first time. I think this is the way you do it, but all right. Actually, this is correct. This is correct. Sorry. So what I'm trying to do right here is, look at this. We actually get this big point right here, and then we get this big point. And you see right here, this right here is a frequency that I'm trying to show you. It's 0.1 times 10 to the minus 3, but I kind of wanted to do, is there a way to lower it? Huh, it won't let me rerun it. I wonder why. Oh, whatever. But point is, you see this sine wave right now? This is like perfect sine wave. And we're actually matching this. So if I wanted to change the frequency by doubling it, double the frequency. Look at that. See how these, like this right here is supposed to be the DC term. This is the slowest signal. Faster, faster, faster. So every time I double the signal, or double the speed, or you see now that's at 4 times speed. Actually, what happens at 5? Oh, yeah, it doesn't exist anymore. 2. Or actually, let's show 3. I don't know if 3 is gonna work. Oh, 3 works. Oh, see, perfect. There we go. So that's what I wanted to show everyone. So now you see this right here, right? And you're like, oh wow, that makes a little more sense. Now you know what's going on. This is a frequency, but I don't know why that's not working. I think my next example right here, yes, this is perfect. So what I'm going to try and walk you through right now is, we want to turn this Fourier transform into something more human readable. So what we're going to do is, this is our DC signal, right? This is our low base signal, and then consequently we're going to have this due to the like mirroring effect. So we want to bring this point and add it right here, this, add it to here, this, etc. So what I have right here is we're looking at the absolute value of all of these things to make sure it's consistent. We don't want to have signals go away. We're going to look at, let's see, we're going to store this variable. Actually, I'll see if I can do this. Valued section, that doesn't do much. I'm going to store this signal from here up to, well, n divided by 2 is 5 plus 1. That gives us 6. So 0, 1, 2, 3, 4, 5. Okay, 6. This is the 6th element. So we're going to save all these points. Figure for stem S X. There we go. So we just stored those points. We just extracted these points into here. And then we know that with the Fourier transform, the single-sided Fourier transform, you can see it's a doubled value. So this one, this adds this will give us 1. This will to here gives us a doubled. So we're going to double the signals from here up to the final point, well, except the final point. So we're just going to double the second element. There we go. We're going to double this guy, this, and this. We leave this alone for some reason, but let me show you this. Boom. So that goes away. There we go. That's exactly what I wanted to show you. So now you see we have our base signal. We have a matching a 1 at this frequency, and then we have that 0.5. But now I can, do I want to do this? Let me show you 2, and then let's play this projection. See that? There you go. And then if we triple the speed, see that? Now we're traveling through time. And that's basically the whole gist of the FFT. If you want to humanly read the code or the actual thing, use this code right here. So I encourage everyone to use this one. Now, what do I have here? So we're actually going to do an FFT, the FFT itself. So, what is this right here? What are we trying to do? I think what you're trying to do right here, and we're at 52 minutes, so we gotta wrap this up. Exponential discrete Fourier series. Well, from what I can tell you, that is literally this right here, and everything we just did for all the previous signals. But the point is, you're just gonna do, actually I think what I did right here is that wait, whatever you did right here is the actual Fourier series. Actually, yeah, I think you're just literally redoing the work for this, all the basis functions you find. So at kk, it's all going to be the same. So this should be easy. And then use whatever you did right here. So the n values just divided by, well, that. I think this is literally a restamp of this. That's literally my opinion. To use the FFT function, so this is why I was saying something about scaling problems. All you got to do is, well, FFT, your actual signal, x, divided by, you got to remember this puppy right here. So the alpha FFT, that's what I'm calling it, it's the FFT, but you have to scale it down by however many points you have. And then once you get the alphas, I did this because they kept doing the, actually I'll show you. So here's our bases. So remember that bases thing we created right here, which is this right here. So we're just multiplying, matrix multiplying it to the alphas that this FFT created. So There you go. This, and it should be the same thing. Boom. You see this orange thing? I have OCPD. Real. There we go. And then it doesn't appear anymore. There you go. See? Looks pretty cool. If you don't do this divided by n, you're gonna get the following. Oh, look, 5. That's not bueno. So you have to normalize your thing by n. And then remember what I just told you about, like, you see how you have half the signal here and half the signal here? To get a 1, all you got to do is exactly that pancake folding that I showed you right here. That's how you do it. And now you can be like, oh, yo, dot distributed, I know how to do an FFT. You'll learn how to build this in 480, so I recommend taking that class. What do I have here? Exercise 6. Signal. Yeah, I think you're just doing FFTs. Yeah, this is literally easy. I'm just doing your assignment, everyone. Boom. But the point that I'm trying to get to you is this special code right here. I want to explain what's going on. So let's do 30 points. Because yes, you're doing your assignment, but I want you to know what's going on. So, okay, without looking at this, I'll just put that away. Why did I do 2 pi frac, or whatever you call it, n, and not this actual raw signal? I could have done like, oh yeah, 2 pi times n divided by 5, but I pulled that right here. What's the frequency? The frequency is 1 divided by 5. What's that? It's 0.2, which means this is going to literally be a signal at 0.2. If you can sing a 0.2 frequency signal, you're probably like a big drum or bass note. And then right here too, well, this one's hard to explain. Actually, you could do the same thing here too. Frick. However, this is a square wave. A square wave has, it has a little more information. It's gonna have like these, like, you know, actually I'll draw this right here. And what gave me OCPD is I didn't put that there. A square wave, if you wanted to do a square wave, you're gonna have harmonics where here's your bass term, which whatever your DC shift is, then maybe the actual bass signal itself, because it's actually periodic. So if you play this on a music scale, here's your like resonate, your like actual what do you call it? It's fundamental frequency. There you go, fundamental frequency. And then you're gonna have all these like shaping frequencies that are like up here. You'll probably see that in like a lot of EDM music. But the point is, if you wanted to generate this happy, nice sine wave, like then its actual Fourier transform is just gonna be the actual fundamental frequency, and that's it, assuming it's like really clean. So to figure out what we're trying to look at, boom, running this, look at that. For the FFT of what are you doing? Oh, let's do the easy one. Y. Look at that, we get that 2.2 hertz. See, and you get a 1. However, if we try to do this square wave, actually, okay, figure 999, and let's do yeah, stem. I was gonna plot, but it's fine. Stem Y. See that? It's a nice, beautiful frequency, and this is what it's gonna look like. However, if we were to do the actual square wave, pull that out. You see, square wave. You can't generate. You need to generate with. To generate this, you need more sine waves, and that's exactly what we have here. Boom. See, you need this base frequency. What's this base? It has a 0.1 DC. A couple of these. Oh, look at that. Why do we have this? Why do we have this? And that comes from a property. It's a famous property. Maybe I can find it. harmonics of a square wave. Let's see if we can find that right here. Here you go. And then you can probably see that. See, we get these harmonics right here that happen to there. I think this one's good. See, fundamental. Yes, I'm getting my lingo right. It's not doubled though. It's okay. Should be fine. But that's what you're seeing right here. See, you get this, but we get this residue because we need more points. We're just literally doing a little bit. Actually, let me show you this. Actually, 15. It's giving you this because it's requiring an even number. It doesn't like odds for some reason. So if you do 16, there we go, goes away. If we do 14, it's still there. Actually, 5. See? Oh. Here's the good thing about doing 5. With the square wave, you actually see the fundamental, and then you see this little residue. Everything else, all the information's gone. Like you wanted to generate the actual square wave. Where is the square wave? Square, where did you go? You want to generate this with this. Psych, never gonna happen. You need more information. So to get that more information, you need more basis functions. See, if you add all these, you can create that. Oh, you can add more. Let's do 40. Boom. And etc. And that's why I did 200. See? And actually, oh, you know what that looks like? That's kind of almost looking like that sync function. You can probably see like a peak up there. And this is actually not that bad. Pretty cool. Actually, we're missing information. Whatever. But that's how you do exercise 6. And then, what do I have here? Let's just run it for fun. Why'd I do this? Oh, that's how you generate it. This is easy. Fundamental. Boom. Boom. Yeah, same thing. And that's why I think this assignment was pushed back for later. But it's a really, really simple assignment. It's basically to get your feet into, well, why we always do these discrete Fourier transforms. But what is a relationship? I'll let you figure that out on your own. But point is, the most important thing I wanted to get to everyone is this. You can create a function for this if you wanted to. You can create a, for those who are daring into MATLAB function, pretty FFT. Maybe I'll create this function, and then you can do all this. Boom. And then you can always have a perfect signal. Actually, you need to have F. There we go. Boom. But we have input. We're expecting a signal and N. Yeah, there we go. So there you go. Boom. Created a function pretty quick. Just kidding. So for those who are very daring into MATLAB, I do recommend doing that. There we go. So with that, I think that's all that I wanted to talk about. Oof, I'm already at a 1 hour and 3 minutes. All right, y'all. So hopefully this was helpful. I think the next video I'll do is on probability because we're already at the end of the semester. But you guys got this. If you need anything, take care.